Hi, this is lesson 13 in the use of JASP and understanding statistics. So in the last couple of sessions, we have been working on reading in data, manipulating data, doing transformations in order to satisfy the normality assumption and the homogeneity of variance assumptions that underlie a very basic t-test. And today we're going to continue to dive deeper into how do we evaluate those transformations that we did previously. So let's start by opening up our computer file. We've been working on a data set called Bank Revised 05, and I'm going to open that up. And this includes changes that I've made in the last few sessions. So, not going to be a lot of rehashing what we did before with the ladder of powers, but we originally had a variable called salary, beginning salary. This variable turns out to be highly skewed, and we tried taking the square root of that, doing a log of that, doing a reciprocal squared, and ranking the variable. And we're going to now look to see how those transformations perform. So what I want to do is to start off, when you're looking at the nature of the distributions for a test, it's good to start off with just doing basic descriptive statistics. And we're going to do this for salary beginning, the square root of that, the log, the reciprocal squared, and the rank. And for my statistics, I want to get skewness and kurtosis and the Shapiro-Wilk test of normality. So I'm going to click on statistics and click those buttons. And I also want to get basic plots, and I want to see the basic distributions. And I want to get the QQ plots. Okay, so here's the original distribution that we have, and as you can see, it was very highly skewed. Looking at this, with the skewness index here is 2.853. A general rule of thumb for problematic skewness is over 1. Same thing with kurtosis, over 1 is considered problematic. And here you have a 12.39. So these are extremely problematic skewness, that is outliers in the right, kurtosis, a whole bunch of values peaking at a particular point. And skewness and kurtosis often go hand in hand and are key to defining a distribution that is not normally distributed. And here you have the Shapiro-Wilk, and it's highly significant. As we're going to see here, though, with the Shapiro-Wilk, all of these are not significant. So the higher the value, the better you are off with the Shapiro-Wilk. And even our best is still not considered normal. But you can see that when I did a square root, let's look at skewness. Square root, skewness drops from 2.8 to 1.9. With a log, it drops from 1.9 to 1.27. With a reciprocal transformation, it drops from 1.27 to 0.313. That's under 1 and looking good. For the reciprocal, now it's starting to go higher in terms of absolute value, and with the rank, it goes again higher. So looking at skewness, this is our best distribution. If we look at the shapes, we can see less skewness and kurtosis, less skewness and kurtosis. Here for the reciprocal, this is our most normal looking distribution. Now it's starting to get problems going the other way, where the skewness is going to the negative side. And with the rank distribution, it's going even further that way. So when we're doing transformations, you're taking something that's right skewed, making it left skewed, but you can overcorrect and then make it left skewed. Um, so you pick the one that's done best, and that's the reciprocal. If we look at our QQ plots, you notice huge, it's supposed to line up along that line. We're not doing that, not doing that. It's getting better. Here we're getting our best version of this, which doesn't look too bad. Here it's starting to overcorrect, go back down, and here very much overcorrecting. So that is a simple way of looking at the distributions to see which one of our transformations did best in dealing with problems of skewness and kurtosis. And we now have a good idea which one that is. Now, if we want to look at this at a deeper level, we can go to distributions, go to normal distribution, go over to generate and display data. So here you tell it what variable you're going to use. It only allows you to look at one variable at a time. So I'm going to go ahead and start with our original untransformed data. And then down over here where it says assess fit, I'm going to click on that. I'm going to go down and I'm going to click on all of these for assessing fit. I have a number of different statistical indices for looking at whether or not the normality assumption has been violated. Again, here we're seeing that here's our distribution, and then there's a normal distribution superimposed, but the normal distribution doesn't go all the way down on the left-hand side because it's really badly fitting. This overage right here is indicating that these spikes above the normal distribution, the observed data above the normal distribution is not fitting the normal distribution. So it's spiked up. This blank spot here gets captured in going underneath the line that where the sample would match theory. And then these data points over here, which this graph is highly sensitive to, is showing that you have outliers that are way beyond what is expected under the normal distribution. Over here, you have the same information, but it's done as a cumulative distribution. This should be a nice S, but the S is cut off. And so what you see is that there's a bunch of data points that are occurring before what is theoretically desirable. It goes up in an undesirable fashion. It finishes off. This one pretty much has to finish off at the where it's supposed to. But it's supposed to line up on that line. It's not doing that. None of these are significant. Let's take the easiest one to look at here. I think that's the Anderson-Darling. It is now showing us at 39. What happens when we start going through? Let's go to the square root transformation. And now things are getting better, but still are bad. The Anderson-Darling has gone from 39 to 26. All of these indices are still significant. So we're going to do the log, and here it is. And Anderson-Darling has gone down to 15. And we're starting to see a little bit more of an S, and these are lining up closer and closer to those blue areas. We're going to go from the log over to the reciprocal. This should be our best, and you notice that we're barely going out of the blue. A little bit here, we're out of the blue, but this is the distribution that fits best. We have more of an S. We have the data lining up on on the theoretical S shaped curve. This is going to be our best bet. Notice that this is still saying that it's significantly not normal. Significantly not normal for all of these tests. But all of these tests, I would argue, are a little bit looking for a little bit too much perfection. And if your data is pretty much aligned within these blue bands, I would not worry about it. There is a little bit of deviation from it, but not a lot. So I would consider this to be satisfying the normal distribution, and it is the best you're going to do. Notice that we can overcorrect if we go to the reciprocal squared. Here's reciprocal squared. And now we're overcorrecting, and it's starting to get bad in some places again. And now the Anderson-Darling is going up from what it was. Its optimal low was 3. And then the rank is your strongest possible one that you can do, and you can see that that really overcorrected and made things highly negatively skewed. And now we see the bottom part of the S, but we don't see the top part of the S. And we have too much data over here where it's not supposed to be, and it doesn't finish out on the lower part of the curve. That non-finishing out is where you get this spike over here. So remember, this graph here corresponds with this, and whether or not the data points are fitting on to the normal distribution. And this graph here is a representation of how the data points are fitting on to the normal distribution, which should appear as an S because it's in its cumulative distribution form. As a cumulative distribution, it can only go up. You can see that the story again was pretty much told simply by looking at your skewness and kurtosis, and that allows us to pick our best fitting distribution. Now, what do we do with that information? I'm going to save that for one more video on this topic, and that's coming up next.